Hi folks, happy Friday. I did something with my knee over the last couple of days, and so this is going to be a very non-dynamic lecture. I'm going to sit here and draw on the screen. Sorry. But that's the way life goes when you get old. So this is where we left off last time. We had taken the physics that I basically just told you about a DC motor and gotten some math out of that, including a differential equation from the free body diagram, as well as some circuit laws for the armature, as well as transmitting the current through the armature into a torque. So those are all encapsulated by these 4 blocks and a summing junction here. Why don't you check your memory and label the signals in this block diagram? Something like that. Across the top, we have the armature current, the torque generated by the motor, followed by the speed of the motor shaft.
If I understand the signal coming out of the KP with is the back VMF.
That's right. So this would have been V back, if you wanted to call it that. Yeah. Good. Any questions on how we got this? Okay. If we were actually interested in the position of the shaft rather than its velocity, would we have to start over? No. What can we do to this block diagram to make the position the output rather than the speed? Integrate. What would be the Laplace way to integrate a signal? Fantastic, my 228 students. I take it all back. Awesome. So let's, and then the next slide, I don't know, I hope I can copy, that'd be nice. Look at that technology. Copy. Paste. Perfect. So step 5 is if you have multiple blocks, which we do, you can almost always reduce them into a single block. Now, a block in this context is a transfer function, right? Every block is a transfer function. What I'm after at the end of the day So our goal down here is the transfer function from VA to theta M, from armature voltage to position. Right? A single transfer function. One polynomial divided by another polynomial. So graphically, what that is going to mean is we're going to basically wrap all of this as a single block, right? That's the goal. Okay, let's start with the easy ones. What can you do with two transfer functions in series or in cascade? Multiply them. If these were impulse responses, you would convolve them, but since they're transfer functions, you get to multiply. That was the nice thing, one of the nice things about Laplace, it turns convolution into multiplication. So instead of having three blocks in series here as separate blocks, I could have one single block where I multiply everything in the existing blocks. So let's go through with an eraser and okay, so we have Km on top and R plus SL times JS plus KF. One box. Where did the motor torque go? That was a signal that we had on this slide. Once I have collapsed or simplified those blocks in cascade, where did that motor torque signal go? It's now internal to that big block. That is, it's still there. There is still a torque physically present, but we don't have access to it anymore in this block diagram. Okay, so there's a minor price to be paid when you collapse these blocks. Okay, let's get my... Good question. So back here, this was, it's not really an error in this case, right? Because this was a system that was a feedback system, but not a control system. So this voltage here is the delta V across the armature, across the R and the SL. So I hesitate to call it an error, but that signal, that delta V signal, is still right here. Before it was the output of the summing junction, it's still the output of the summing junction. We haven't touched the summing junction. It's the same signal. Yeah. Okay. Let's I want a blank slide. There we go. Okay. So what we have now is, well, we've got another block out here. What can I do with that? Is that in cascade with anything? No. It's because of this pickoff point that it's not cascade, it's not in series with the big block that we just simplified. Okay, so don't get carried away. That's what I'm trying to say here. So remember, what we're after is a big box around the whole thing. And we can't take the 1 over S and simplify it. So we need to try and simplify the feedback loop. Okay. And that is so important that it gets its own blank slide. So sidebar here, what happens when we have a system that looks like this? I'll call this X, I'll call this Y, and I'll call this E. So if you want, you could title this in your slide, simplifying or reducing a feedback loop. You are going to be doing this, not this derivation, but you're going to use this result in every problem that comes in this class, essentially. Okay, and remember the goal is a single block between X and Y, right? So how do we get from there to there? That's the question. And the simple answer is it's easiest to do it with algebra, to do this derivation, just algebraically. So what does Y equal? That is exactly where we're going. If you don't see that, a simpler answer would be E times G. But we're about to do what Miles just said. Y is the output of G. What is the input to G? E. So I guess to remind you, we're doing this all in Laplace, which is why we can multiply inputs with transfer functions. So then the follow-up that I was going to ask is, how do I write E? E is the difference between X and this thing, which we could write as H times Y. Okay, so I'm going to take this and I'm going to sub it into here, which gives me Y of S is G times all of this stuff. So X G minus Y G H. Collect the Y stuff on one side, collect the X stuff on the other side. And we get what, plus G H and X G. Please finish the derivation. Triple box, that's how important this is. So when you have a feedback loop in a block diagram, you can reduce that feedback loop to the forward path transfer function divided by 1 plus the forward path transfer function times the feedback path transfer function. Okay. A couple of things to note is that this minus sign turns into a plus sign here. Okay, so what we derived was for negative feedback, which is 99% of all feedback cases. But it's kind of handy to know that if this were positive feedback, the denominator sign would flip. And you could prove that. I mean, it would just redo the algebra with the opposite sign. Questions on that? Okay, with that under our belts, let's go back to our example. What is G in this system?
Big.
The big box. What is H in this system? Good. Does 1 over S play into this at all? Not the feedback loop simplification. So we've got all our players well identified. So let's implement our fancy trick, which is going to do what to our diagram? It's going to take, well, I'm not going to be able to remember that. So I'll do it down here and I'll copy it up. We get forward path. For 1 plus forward path, that same thing. Times feedback. And so that replaces all of this. Pretty cool. I mean, messy, but pretty cool.
That feedback doesn't change the units of anything, like the omega m, that's what omega m.
Yeah, because over here, X was in, X is still in, Y was out, Y was still out. X and Y haven't been touched. It's just the stuff between them. So the signals, it's actually critical that the signals remain the exact same through this entire operation. Okay. Okay, so I think we're ready to accomplish our goal, which is the VA to theta M transfer function. Well, in this class, you're going to end up with a lot of nested fractions because of the rule that we just derived, right? G and H are generally going to be fractions, and we've got fractions of fractions. So you're going to be practicing your simplification of fractions quite a bit. And what I'm going to do very, very often is take a look at this quantity and note that it appears here. So if I were to multiply this big fraction by this red blob divided by this red blob, i.e. multiply by 1, then both of those red blobs go away, and I get a copy of the red blob here. Okay, so that's what I'm about to, it's messy to do, but it's kind of easier to say. So that's why I gave you a warning beforehand. So I get Km alone on top, and I get that R plus SL JS plus KF, where the 1 used to be, and I get Km, KB, O, and by the way, there's the 1 over S as well. So there's our final answer. Take a step back and think about what just happened. We now have a way to map how the armature voltage signal, which we ostensibly can control, affects the position of the motor, right? We have an end-to-end view of that, and we've kind of black boxed all of the internal stuff away. Not black box, because you can see inside, we can go unpack what we just did, but if the next person in line that works with this stuff doesn't care about the armature current, they don't have to be exposed to it. Right? We can just give them this transfer function. This transfers the input to the output. Job done. Questions? There's a couple more things we can kind of wring out of this example. So I'm going to scroll back to the kind of initial block diagram. Where are where are the poles? Because there are various subsystems here, and those subsystems have poles and zeros. Well, they don't have any zeros, but where are the poles of the subsystems? Can anyone identify them? One is at 0, pole at 0. Good. Negative R over L. Excellent. Any others? Not of the subsystems, right? We've got all the subsystems that have S's in them, and we have identified their poles. They have no zeros. So we are eventually going to come to call these the open loop poles of the system. One is at negative R over L, one is at negative K over J, and one is at 0. That's exactly where the name comes from. Yeah. The idea is if we were to either break the feedback here or actually technically more correctly break the feedback there, these are the poles that we would be left with. And the fact that they are where they are is not super important. The fact that these both have negative signs on them will become important. But the follow-up question is, where are the poles of this transfer function? Or perhaps more easily, where are they not?
Yes.
Yeah, they can't be at the same R over L and K over J because of this term, right? If that term were 0, then yes, they would be the exact same place. But because we have this extra constant term that's changing the polynomial, which changes its roots locations. So the big takeaway here is that the open loop poles have moved. And that's pretty much where I want to leave it for now. Like that's sufficient that you know that much for now. The pole at the origin has stuck where it was. And that's mostly because it was outside of the feedback loop. It was just cascaded with our feedback loop. So the takeaway is that the feedback loop moves the poles. Does it make them better or worse, or what does that mean? Those questions I hope to answer in the next 3 weeks. One. Correct. I would not call this an open loop pole. Mostly because it doesn't move when we collapse the loop. The pole at the origin, this guy. All right. So your textbook has a big old table with a bunch of block diagram reduction rules. I think this gives this stuff more credit than is actually due. It's just algebra done pictorially, right? How did we derive the feedback loop? We transformed it back into algebra and then did the algebra. So the cascade one you guys already got. That technically means that the order doesn't matter, because if you're multiplying, it doesn't matter what order you will multiply in. So that's what they're trying to say here. It could be G1, G2 or G2, G1. And just to show you that this is just all algebra written pictorially, I want to go through this one. So an expression for x3 in this first diagram is that it is G times this signal. Who can give me an expression for that signal? What goes in the parentheses here? Good. X1 plus or minus X2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2 This X3 is going to be the sum, or I guess the sum or difference of this signal plus or minus this signal. The first signal is X1 times G. The second signal is X2 times G. Are those equivalent? Yes, that's how we get this block diagram equivalence, is we do the algebra and then find out what it does to the picture. Okay. So I think students have the tendency to like treat this table as magic. It's not magic, it's just algebra. And the table continues, including our favorite reduction rule here. Sure.
So I see the plus minus, like the feedback, what's in it? I don't understand what a positive feedback.
When you do something, I say good job, and that is then positive feedback. And then you keep doing that. And I say good job, and you do more of that. And I say good job, and you do even more of that. Which in learning and in social contexts is fine and good often, but in electromechanical systems, that's often bad. Because it would be, okay, you've moved the car has gotten to 60. Great. Now it's at 65. Good job. You're going super fast. Now it's at 70, right? So like, yeah. So this we'll get to talk about this in stability. But yeah, this is why I was saying most feedback loops, if the goal is a stable system, are negative feedback loops, but the math works out the same. Yeah. All right, let's call a little audible here. I'm going to do something that's not in the slides. Okay. We've talked about the kind of canonical or the common form of a control system. We had a controller here. We had an actuator here. We had a plant or a process here. And we had an output here. And we had a measurement device here. What I'd like to do now is talk about what if we have multiple inputs to the system? Multiple inputs. So we'll give it a negative feedback, but for the rest of these, I'm going to omit the signs, and the implication is that they are plus, 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 plus. So let's call this one a disturbance on the U signal. Let's call this a disturbance on the actuation signal. And let's call this noise. This is what? That's a bit of a philosophical issue. If you're not measuring it, is there noise? But from a practical, if a radio is on in the forest, is there static? No, from a practical point of view, we only see the noise once we measure it. And so let's model it as coming in after. The lesson here won't change if you put it beforehand. And I'm sure there are reasons out there why you might want to do that. But for the most, like in a communication system, we say we transmit noise free and we receive noisy. So the noise came in the channel in the transmission. Yeah. Okay, so this is a multiple input, single output system, or MISO.
DA just keep going.
I was gonna teach you that. If I want the transfer function from R to Y, which I think Lawrence was getting at, the transfer function from R to Y is like an interpretation of that is the effect of R on Y. Right? We don't really say it like that because it takes too long, but transferring R to Y is how does Y change with R? Okay. If C is LTI, if A is LTI, if P is LTI, and if M is LTI, is this whole system LTI? Yeah, in particular, we just got a Laplace transfer function, which implies LTI-ness, right? We did the whole feedback loop collapse. So this whole thing is LTI. And what is the most powerful property of linear systems? I guess it's up for debate, but I was hoping you would all say superposition in unison, where your voices superimpose on my eardrums. No, the time has passed. Linear systems obey superposition, right? You've learned this in circuits where you had multiple independent sources. You've learned this in 228 where we had one source that could take different values and we can add them together. I want you to think of this more in line of your circuits superposition problems, where to find the effect of one source on the output, we turned the other sources off. And then we repeated that for all the sources. So what does it mean to turn the other sources off, Lawrence? Sure. Make them equal to 0, I think is a more accurate way of saying that. So if I set du equal to 0 and dA equal to 0 and n equal to 0, if I do that, do I need summing junctions? Because I'm adding 0. So the summing junctions just disappear. This is only to get the effect of R on Y. Okay, so by setting these disturbances and noise sources to 0, I can say that the transfer function from R to Y is CAP over 1 plus CAPM. You are going to have 8 different cases. I would like you to find the transfer function from du to y. So your assignment is find this. Go.
I thought. Yeah. We shouldn't be. But you're saying that feedback doesn't back this loop. Like, so here,
Okay, so I guess. It's going very good. This guy is, this guy is, this guy also is. Big old diagram. You coming in. All these guys. That is correct. That's. This is negative feedback. No, you said it's 0, but you're. I'm lost in sleep. Sure. Choose. This. Oh, it's begin with the first part, you know, recomes. And with this being that age. Substitute for C. C equals. I had a kind of say. Oh, I just thought or yeah. Is now the. I think that, yeah, I think. Oh. Yes. I mean, you know. There's institutional to.
Yeah, that, no, I heard that.
This is strong. Several years out. They were trying these origin signals. Yeah, it's. So it would be. On. Yeah. But subtraction. It's the same as subtraction. Yeah. Linux relationship. Yeah, this is. It's very. Yeah. Most of it. Yes. Not good. Okay. Why is it negative? Negative feedback, yes, yes.
Trying to find this. I don't know these things. Absolutely.
I like the all the exchange with the.
That's why.
Oh, that's right. See, this, you can get rid of the T box where you just move that, that. That's how I play it. But some of the old with the first thing, just keep asking for DU. So, right, so it's like, you know. Or and that was still never told why that not. I did go back and see this. But bonus is you know based off someone's. It's working. So I was thinking,
One. Oh. Right. Yeah. Okay, so we. Oh, you should put it in. Wait. So what's the zero? Yeah. Oh, it's that. It's. So it's yes, then. Just. Well, that, I think that.
One of the big takeaways of this exercise is to convince you that block diagrams are mutable. You can bend them around, you can draw the same diagram in different ways and they're equivalent. The black diagram, R is the obvious input, quote unquote, and Y is the output. But if I want to focus on DU, I am within my rights to have DU come in from the left, if that helps you. Okay, so I have kind of implicitly set dA equal to 0 and N equal to 0, and I've gotten the red diagram. But I want to convince you because this is mildly important. When I set R equal to 0, then if I call this signal, say Y measured, what should I call this signal? Yeah, the negative of Y measured, because it is literally 0 minus Y measured. Because I've set I set R equal to 0. Okay, so that means, and how should I best do this? I'm going to take this whole mess and I'm going to replace it with a multiply by -1 gain. Okay, because it is what you just told me we're doing. That -1 gain could sit between C and M, or it could move after C. Right? Because the order in which we do things in series doesn't matter. So I'm going to move that there. And instead of draw it in a triangle, I'm going to move it here and make that a minus. Okay, this is I hesitate to call the sound rigorous, but this is the rigorous way of showing that we still get negative feedback. Okay. All right, and so now I hope the diagram is more clear that we get the forward path AP over 1 plus the forward path times the feedback path. Questions? Meh. If it's got no dynamics, if it's not a function of S, you are within your rights to put it in a triangle. If it is a function of S, like an honest to goodness transfer function, well, if it's a system with dynamics, then you should put it in a box. Yeah. What is similar between this transfer function and this transfer function? What do they have in common? No. Their denominators are the exact same. That is not an accident. Okay. What does that mean about their poles? They also must be the exact same. So it doesn't matter which input-output pair we're looking at. The poles of a closed loop system are the poles, regardless of which IO pair we're talking about. And that is kind of cool. Closed loop poles just are. It doesn't matter which IO pair we're talking about.
This.
I think the black is one way, the red is another way.
Property.
The only properties I used was cascading. A in series with P becomes AP, and feedback loop, forward over 1 plus forward times feedback. I didn't have to use any of the jumpy pick-off pointy kind of deals because the block diagram wasn't that complicated. Yep. It's just multiplication, so put it in whatever order you like. Yeah, yeah. I implicitly used superposition where I set the other inputs to 0. And if I set dA equal to 0, if I call this signal X, what is a good name for this signal? Yeah, X plus 0. So exactly, yeah.
This is new initial condition.
No. No, initial conditions count as initial conditions. Right. And that's the flippant way to answer that. The more serious professional way to answer that would be disturbance is an exogenous input. It comes from outside the system, which is actually the definition of what an initial condition is not. Initial condition comes from inside the system. So yeah, I would not model them as external disturbances.
That's still another signal that you would short.
You are thinking of how like capacitors with initial voltage appear as a voltage source in Laplace? Is that kind of what you're getting at? They do. So if we had a circuit and we had an initial condition that we had to track, we could track the effect of that initial condition on the output and get I hesitate to call it a transfer function because we're not transferring an exogenous input to output, but yeah, you could do something like that. Yeah. Yeah.
Why did he get
DU is always in front of C.
RS being out?
Yeah, you can set that to 0. This signal is still the negative of this signal. So everything that I said still applies. This whole thing becomes a -1 multiplier. And I get the same diagram, except it's on its head or on its side, I guess. This is one of those things where I can do a bunch of examples, but you won't benefit until you do a bunch of examples and redraw block diagrams and make them work for you. So, I mean, see homework 1 for examples of this. Okay. Is there any more I could fit in 1 minute? I doubt it.
It's the same denominator.
For sure, that could be an error check on your part. Like you need to get the same polls no matter how you do it. Have a lovely weekend. We'll finish module 1 on Monday, but nothing in the homework requires Monday's lecture.
So,
Yeah.
yeah.